Hello and welcome to today's Interface Fluidics webinar, Dealing with Supply Chain Issues, Making Chemical Decisions Within Constraints. Our speaker today is Stuart Kinnear, co-founder and CEO of Interface Fluidics. With over a decade leading teams in the oil and gas industry, Stuart brings an extensive background in business intelligence, supply management, and contract negotiations.
So when we started putting together this topic for discussion, it really is a result of a lot of our customers coming to us to try and find solutions to some of their supply chain issues. And if I think back to my previous life as a supply chain manager, when I think about what issues mean, it's really four broad categories: price, availability, service, and then environmental or efficiency concerns that might be a goal. So like I said, we're doing this because I hear the same comments from our customers on a repeated basis over the last year. Questions like, my friction reducer has gone up in price and I'm looking to control my costs. The chemistry we selected is no longer available and I need to find a solution quickly. I can't or won't truck in fresh water for my frac, so I'm looking to find chemistry that is salt tolerant so I can use produced water. Or I'm seeking to switch to a bio-based product to reduce my emissions profile. How do I pick from the products that are on the market today? So these are the questions I'm going to hopefully be able to give you some solutions to throughout this webinar. Now, before we get into our specific solution, I wanted to go over an overview of how we compare an interface to the traditional way of solving these problems. So if I go back to the questions that our clients ask, my friction reducer has gone up in price. I'm looking to control my costs. The way you can screen for new friction reducers that may be more available or more cost effective is traditionally done through prop and pack testing or core flooding. Both of those have significant drawbacks of being not particularly repeatable and quick, or you can have a repeatable test that is going to take weeks to do just one measurement. So at Interface, our regain conductivity solution allows you to get the quick, repeatable answer that you need in order to make a decision quickly. This goes for the same issue around chemical no longer being available. If you want to find a salt tolerant product, like a surfactant that's salt tolerant, typically you'd look at a column drainage test, bottle testing to ensure no emulsification issues, or you might look to an Amit cell or a core flooding. Again, none of these tests really offer the fast and repeatable turnaround that you'd get with a microfluidic solution. Now at Interface, we use a technology called reservoir analogs, which are a microfluidic technology. And we create analogs that match our client's reservoir so that we're screening those chemistries based on their particular reservoir or well. We're optimizing for things like pore throat sizes, porosities, permeabilities. We make sure we get the wettability correct. And then we're fully vertically integrated. So we go from design all the way through fabrication, do the analysis, and present a decision-ready data set for our clients when they're approaching us with these challenges. If you'd like to learn more about our analog design process, we have an extensive webinar on that process of actually matching our clients' reservoirs. So I'll keep going. Today, I'll present 3 case studies of how we helped a client screen or select a new product. The first was a project we did for Saudi Aramco, where they were looking for CO2 mobility control using supercritical CO2 at representative reservoir conditions. So the client came to us with the goal of qualifying a suite of foaming agents for compatibility with supercritical CO2 and the brines of concern at reservoir temperature and pressure. They're seeking a product that creates a highly stable foam in a salty water solution at reservoir relevant temperatures and pressures. And traditional foam analysis tools were not able to capture the behavior under pore scale confinement, and core flooding only provided them with indirect performance measurements rather than the direct performance measurements that microfluidics would be able to provide. So for this project, their goals were to measure the foam half-life of 6 different surfactants in 2 different brines under realistic confinement of their reservoir and compare those to the bulk scale measurements that they'd already done, as well as quantifying the effect of varying the brine composition and foam quality on various surfactants performance. As I mentioned, in this case, we designed an analog that had representative permeabilities, pore throat sizes, and porosities. As well, you can see upstream of that porous media, we've got a foam generator. So this was a custom solution for Aramco that delivered some really excellent data. So for our first stage of foam screening, we're looking for the foam stability or half-life of the foams that were put through this porous media. And a high-performing surfactant in this case should have many lamella, and that lamella count should be as stable as possible over time. So you can see for surfactant 1, the green dotted line has the lowest slope at the highest number of lamella. That was the highest performing in that case. And then if we look at surfactant 2, we had different performance of different chemistry, and there are some other considerations to picking the best product in that case. If we then go on to the pressure drops, so we're looking at the effective viscosity of these foams. And so we're looking at here, the graph you're looking at is the pressure drop across the porous media on the y-axis, and the foam quality, which is the ratio of the liquid to gas phase or liquid to supercritical CO2 phase in here. So you can see we've conducted a significant number of experiments which allowed us to effectively differentiate different surfactants from each other, as well as differentiate how the brine was going to affect the performance of that foam. So at the end of that project, there was a lot more information that we collected, but those were the highlights. That results were published in Nature Scientific Reports. And you can see here we ran more than 42 individual experiments in just a few weeks. That's the equivalent of years of core flooding work. It allowed us to capture accurate differentiation of high-performing products and allow Aramco to down select for further testing in their facilities in other laboratory experiments. And we did compare the results to the traditional foam loop rheometer that was used, as well as the core flood, and found to be comparable results. So it was this solution was an effective replacement for those tools and increased the speed and accuracy of the results. And as I mentioned, you can look at the full report and the full paper that was published in Nature last year. We move on to a second client example here, where we're screening new surfactants to help them reduce their costs. Interface partnered with Primex Energy Partners on this project, and we thank them for contributing the results here. So Primex Energy Partners is a Permian Basin producer with wells of interest in the Wolfcamp B formation. The client is including surfactant additives in their fracturing fluid package on each well in order to modify wettability and increase production. The client had many choices of surfactant producer and was seeking a third-party validation of claims from those chemical suppliers for a field pilot. So their goals in this project were to screen a significant number of different surfactant products from different producers, and then verify that the manufacturer recommended loadings lined up with the performance that was required. So Interface used our custom flowback analogs in this case that were, the experiments were conducted at 150 degrees Fahrenheit and 3,300 PSI pressure, which is representative of that reservoir, in a 85 nanometer pore throat Wolfcamp B analog with reservoir oil provided by Primex. We were comparing the results of the surfactants to a control case of base fluid with no surfactant in it. And we're looking for a high-performing product that produces the highest volume of oil flowed back. So that's your primary performance indicator here. Primex was previously completing their wells with the chemistry sample P4 at the conditions outlined in test 12. So they're injecting at 1.5 gallons per thousand. And you can see in that case, that is not that was far from the highest performing product in this test matrix. After we ran a number of these experiments over a few weeks, we found that sample P7 in both the high loading and low loading case performed the best, significantly outperforming the product that was previously being used as well as the control. The interesting finding here is that this product actually performed better when the concentration was reduced by 3 times versus the manufacturer's selected loading. Once we had provided these results to Primex, they then completed a new partner well to the first well with similar properties and with the recommendations that Interface had made. So we're comparing the gray line, which is the original well, to the blue line, which is the well drilled and completed with Interface's recommendations. The takeaways from this graph are that you can see the first oil and peak oil were both achieved 50% faster without any degradation of the productivity of those wells. So the conclusions that we came to from answering this client's questions were that manufacturer recommended loadings were higher than needed in order to achieve a high performance in that reservoir. As I said, first and peak oil were both reached 50% faster with the new chemistry. And switching chemistry resulted in a cost savings of more than 60% on a per well basis. And that one well returned at 12 times return on their investment on the project with us. So for our final case study today, I can't share the producer that we worked with, but we were looking at a polymer flood enhanced oil recovery project. So this is a high viscosity oil in a low temperature reservoir that has already been under polymer flood for a significant period of time. The client was seeking to reduce the operating cost of their field without impacting the production negatively. So I had 2 questions coming into the project. The first was, does polymer viscosity matter primarily during the early injection phase of a reservoir, and can viscosity potentially be reduced in order to increase injectivity and reduce operating cost? The second was, could a similar or better performing product be identified and de-risked very quickly? So I'm going to show you 2 sets of videos here comparing in this case, we're looking at a high loading and a low loading of the same polymer, one at 50 centipoise viscosity and the second at 20 centipoise viscosity. As I play the video here, what you're going to see is that the 50 centipoise viscosity oil or polymer produces significantly more oil early on in the process, but after a period of time, the 20 centipoise oil catches up with the recovery factor. So we can see that if the speed to recovery is the most important factor, a higher loading may make sense. But if we're looking for an opportunity to lower our cost, likely the 20 centipoise polymer is going to perform similarly in a well-depleted reservoir. The second case here, we're comparing. Oh, I've got the wrong video showing up here. I think. Next slide. Next slide. There we go. In this project, the client was also looking for screening alternatives to the polymer that is already being injected. So they came to us with a polymer that had a significantly lower cost and wanted to screen its performance against the 50 centipoise polymer already being injected. So we can see as we inject this product, actually the low cost chemistry and the current product had very, very similar performance throughout the experiments, which gave them confidence that there's a possibility to significantly lower the cost without impacting production. So to conclude this case study, recovery, pressure data, and image processing were all used to characterize the chemical performance and to compare to field data. What we found after looking at production from the field and comparing that to the microfluidic results was that we were able to accurately predict field results with these microfluidic studies. The 20 CP and 50 CP polymers had similar ultimate recovery, but the 50 CP had an increased production rate early on. And the lower price chemistry performed as well as the 50 centipoise polymer and had similar injectivity performance. The lower price chemistry was expected to reduce their monthly polymer spend by more than 50% if it was implemented in the field. So with that, I just want to wrap it back around to some of the questions and how our solutions answer those questions. So our fracturing fluid optimizations for friction reducers, HVFR, surfactants, and other additives can be screened in just a few weeks, as opposed to the months or potentially years if you wanted to run with alternative lab methods. We do have a great relationship with all the major chemical vendors that are out there, and we've tested most, if not all, categories of products that are on the market today. There's always new interesting stuff coming up though. And just to put a fine point on it, our solution isn't just about saving money. It's about finding the right product for the right well at the right time. And with that, I'll say thanks a lot and open up this to questions.
All right, we do have a couple of questions here in the private chat. So when is the best time to engage with Interface for selecting chemistries?
So I would, as early as possible is always the stock answer, but realistically, you can see here we've got folks that are engaging with us from a screening perspective, from a switching perspective, or from a optimization perspective. So we can really help out at any stage, but we think we add the most value during that screening phase so that you don't end up overspending or overcapitalizing in the field.
And what's your turnaround time for a project start?
So if we wanted to start a screening process for a polymer flood, usually we can start within a week or two. Typically, we're able to start the day after we receive the samples in the lab.
Okay, well, thank you all for joining us today. Just as a reminder, this will also be posted on our YouTube channel later if you'd like to share the link with anyone. And you can also find previous webinars also on our YouTube. So thank you for joining us today. Have a good day.
Thanks very much.